Hello, I'm Yasha from Bar-Ilan University, Israel. You're watching a series of lectures on philosophy and methodology of science. We are going through the experiment of low temperature measurement of superconductivity. This lecture is about data analysis of the experiment. Just to remind, our research question is in what way energy loss Q in wires made of magnesium diborate depend on frequency, current amplitude, and temperature. So what do we expect from the measurement? We know from the literature that increasing temperature T should increase energy loss because it decreases critical current in superconductor. Increasing frequency should not affect energy loss in pure superconductor, and energy loss is approximately proportional to I cubic. So what is our sample? First we measure the MGP2 wire produced by Columbus superconductor. It has 1.3 millimeters in diameter. It has 36 superconducting filaments. These are the dark dots, and it has a monel sheet that holds together all the superconducting parts. Monel is a type of copper-nickel alloy, and our specimen is 50 millimeters length. Our expectations were about pure superconductors, but produced wire available in industry, it's not pure superconductor because of technology of production and mechanical consideration and so on. And this cannot be divided. So we are about to measure the whole wire with the interaction of the metallic material and the superconductor. So after the thousands of measurements, we get this plot of energy loss on the z-axis as a function of frequency and current amplitude. So the higher the frequency and the higher the current, the energy loss is higher as well. But in the dependency on those is not similar. So first of all, to make this data more clear and understandable, we have those two graphs for both for the same temperature of 10 Kelvin. The left one is for DC current of 0 amperes, no DC current, and the right for 40 amps of current. The x-axis is frequency, and y is the energy loss. So what we can see that, as I mentioned, the energy loss is higher for every amplitude, which is represented by different lines, curves here. In this area, the energy loss is very linear and as a function of frequency. But for lower frequencies, the dependency is different. There is some different curvature of it. And surprisingly, when we put more current, we add a DC current of 40 amperes, the overall energy loss is reduced. And this low frequency area also changed its shape. However, the overall dependency on frequency is the same. That's a quite surprising result, because usually when we add more current, the energy should be higher. To compare those two cases, I want to show you the loss reduction from the case with the DC current and without. So we can see the reduction is about 50%, which is a huge number, but it's not constant. It depends on frequency from one point, and it depends on current amplitude from another. these results are quite counterintuitive, because there is some interrelationship between the current, the DC current, the frequency, and they affect each other in this case. The other thing we checked is the amplitude dependency. In pure superconductor, the current amplitude dependency should be amplitude in power of 3. But in fact, we have more close to power of 2, and still it's different for the case with no DC current and with case with DC biased current. That's a challenging result to explain. So let's look at the temperature and the DC current dependency. I've chosen 2 points with this frequency and that. They are very different from one from another. The AC current amplitude is the same for both plots. And here we see the energy losses as a function of the DC current and the temperature. Just to remind that the AC amplitude is equal for both cases. So what we see here, for every DC current, we see the temperature dependency is not monotonically increasing as was expected. We see this huge bump on the lower temperatures in both cases, and after this point, the energy loss increases with the temperature, as we would expect. The additional phenomenon is that the energy loss decreased dramatically, as we saw it before, with the DC current. So we see this reduction till this point, and then it reaches some kind of plateau. These results were very unexpected for us, since we expected an increase in the energy losses, and it presented in slightly different way for both frequencies, and of course for every other frequency as well. It's possible to present it all the degrees of freedom here. So the aim of the analysis is to draw a conclusion together with the other observation. The researcher might generalize the result to a wider phenomenon if there is no indication of confounding variables polluting the result. If the researcher suspects that the effects stem from a different variable than the independent variable, further investigation is needed to gauge the validity of the results. So what actually we have here in this experiment? We see that the frequency dependency indicates a non-superconducting loss mechanism. Because we expected that the energy loss does not depend on frequency, and we see it depend very much. Energy loss behavior is different for low and high frequencies. We see the crossover from 2 different regimes in the energy loss plots, and surprisingly, the DC and AC current superposition reduces the energy loss. The AC current dependency approximately proportional to I square and not I cubic, and temperature dependency is not monotonic as well. So we have a lot of things that are not as expected during our experiment design. Are they coming from the wrong design, wrong measurement, or is it a true experiment that there is some additional phenomena that we didn't take into account? To try to understand this, we took another tape, MGB2 wire, with a different material. we have these dark areas. This is the superconducting material, but it's enclosed with a titanium sheath. These are the dimensions in 19 filaments. It's a different wire, but what we wanted to see here, if the behavior for energy losses would be the same or different. And what we have discovered is this. First of all, the DC current does not affect the energy loss at all. The graphs are the same. As we know, DC current does not produce energy losses in superconductor because there is no change. So only the alternating part would. And this is clearly seen in this example. In addition, we see for lower frequency, the energy loss is quite stable and constant. And at some point, it crosses over, and then there is a strong frequency dependence for energy losses. This indicates that the metallic material around the superconductor it plays a crucial role in the energy loss here, and that is the thing we didn't take into account properly when we designed our experiment. So we see the energy loss for titanium are constant as expected. After around 1 kilohertz, there is a crossover to the different energy loss mechanism. Superposition of DC and AC current does not change energy loss as expected, and AC current dependency approximately proportional to I cubic for low frequency, but crosses over to I square with the frequency increase. As I said, metallic component of the wire might affect energy loss in a very pronounced way, as well as geometry of the wire and the number of filaments and the configuration of the wire itself can play a significant role in energy loss. Because of these new discoveries, we have to take the metallic part of the superconducting wire into account. So the properties of the wire of this metallic material play a significant role in the energy losses. So we have to conduct an additional experiments to redesign our experiment and the measurement techniques to take this into account, which is not an easy task, I have to say, because this material cannot be separated from the wire, from the superconducting material. It's virtually impossible to do. And what we measure in this, using this method, electrical method, we measure overall energy losses of the wire. We cannot distinguish what part comes from the superconducting losses and what part due to interaction with the metallic materials. So we have to redesign our experiment. And this is what I'm going to talk about in the next lecture. Thank you.